Hey guys, this is an unexpected video notes. I am leaving in 15 minutes to go see my doctor. I suspect that I have strep throat. My ears hurt like crazy and my throat definitely hurt like crazy. So this was supposed to be lecture in class, but here is our video, so this way you can finish up your homework. Homework is still due tomorrow, okay? So the last time I believe that we have the last, this is the properties of continuity, okay? So we have number 5 left to fill out, and then we have the composite of continuous function property as well. So we'll fill those two out, and then we will do the last two examples. I believe the last one we left off was the constant multiple. So constant multiples. What that means is that if you have k times your f function, keep in mind what f was before, okay? For any number k. So when you multiply any constant to your function, and remember f was continuous at c, so when you multiply the constant, constant k, sorry, I'm having a hard time talking just because I can't swallow. It hurts so bad. So when you multiply any number to the f function, which was, remember, as we defined earlier, was continuous at an x value c, it's still going to be continuous at x equals c. So let's move on to the composition of continuous function. If you remember, the composition was denoted as f composed with g. Remember this? Or f of g of x. Okay, so that's the notation for composition. So this is how it's gonna go. If f is continuous at c and g is continuous at f of c, okay, then the composition, which is denoted as f bubble g f, okay, or you can think of it as g of f of x, just like that, okay. Then the composition g composed with f, or g of f of x, is continuous at c. So we know this right here, it's true, right? If f is continuous c. Well, this one right here, it's kind of confusing. Why is g continuous at f of c? So let's talk about f really quickly. So if I have an f function, oh, you know what? Let's just use algebraic function instead of graphical. I'm gonna give you an algebra equation. So i.e. f of x is, let's say, x squared. Okay, it's continuous anywhere, so that's really not important. So what if I give you g of x? Let's use a different color. Let's say g of x is, let's say, I'm making this up, x plus 1, okay? So the first thing is that, hey, is f continuous at c? So let's pick a c value. Let c be 2, okay? Sure, check, okay? F is definitely continuous at c. So why is this that g is continuous at f of c? Okay, well, let's find what f of c is. F of c is c, it happens to be 2, okay? F of c is 4, okay? So when it says, hey, this is really what f of c is, would you agree? So is g continuous? Is g continuous at x equals 4? Question mark? Because that's what f of c is, right? So, okay, let's see. When x is 4, right? This is 5. So of course, G is continuous. Check. So if it is true, okay, so if F is continuous C, which we let C be any random number here, okay, and G is continuous at the output, so this is output, okay, then the composition is going to be continuous at C as well. And the reason why that G has to be continuous at F of C is because G of F of X, okay, well, F of X is the input, okay, so this is the input, oh gosh, sorry, it's the input of G now, right? So, and the input is where it needs to be continuous at, right? So its input is the location, horizontal location, I should say. Just like this one, F is the function, C is the input, a horizontal value that it needs to be continuous at. So that's why G is continuous at F of C. Then the composition would be continuous at C as well. Okay, so hopefully, if you have more questions on that, please do ask when I return to school. Example 4, give a formula for the extended function for f of x equals x to the third minus 1, all divided by x squared minus 1. Would you agree right now there is a discontinuity at x equals 1? Okay. Why is it a discontinuity? Because when I plug in 1 for x, the denominator is 0. Okay, that causes a discontinuity. So remember, there are 4 different types of discontinuity. Right now, I would like for you to give me an extended function that is continuous at that value that I said it's supposed to be discontinuous. Remember how you asked me before, like, hey, how do I patch the hole to make it continuous, or how do I remove the hole? This is a version of how to patch the hole. Okay, it's not exactly patching the hole using the same equation, but it's making it continuous at the location that we have stated that is not supposed to be continuous. So what do? This is pretty easy. What we would like to do is, when possible, factor it out. So on the top is the difference of 2 cubes. So when you factor it out, hopefully we remember how to factor the difference of 2 cubes, okay? So on the bottom is the difference of squares. So we are going to factor this out. So notice how now I can cancel this discontinuity, okay? So guess what? The leftover function is the extended, okay? The leftover function is the extended function that is now continuous at x equals 1. It might not, this extended function might not be continuous at x equals to negative 1, but it's definitely continuous at x equals 1. So this is our final answer. Now, in the case where you cannot factor and cancel, there are other ways of doing it. For example, you can write it piecewise. You can also rationalize the numerator and denominator to get an extended function, okay? So this is not the only method. So don't, when you do your homework, try a few different things. First, factor and cancel to get your extended function. In the case where that's not possible, write a piecewise. In the case where those two are not possible, then rationalize the numerator, or sometimes the denominator, to get your extended function. Okay. Last example of this unit. Sketch a possible graph for a function f. F of negative 2 exists. Okay, so let's start with our coordinate plane. Looks like I need negative 2, so I need more of a negative side. 1, 2. Okay, it says it exists. That means it has a value. How about we put it at where? And let's keep on going, I guess. The limit as x approaches negative 2 from the right is exactly the same as f of negative 2. Okay, well, how about we make negative 2 positive 2, because it exists, right? And the limit approaching from the right side is identical, okay, to f of negative 2. That works. But the limit does not exist at x equals negative 2. So what that means is that I just have, how about down here? I just have a function, okay, that doesn't have a limit at x equals negative 2 because the left limit and the right limit are not the same. Excuse me. Okay, this is the end of my video notes. Have a wonderful day, and I will see you when I come back. Sorry for sounding so strange and not my best.